Hello and welcome to this FMSP online revision recording for the OCR specification module M2 Mechanics. And the topic is Centre of Mass. Well, let's look and see what the specification says about centre of mass. First of all, that we should use the result that the effect of gravity on a rigid body, maybe some complicated shape, is equivalent to one single force acting at the centre of mass of the body. Secondly, that we can identify the centre of mass if it's a straightforward uniform shape by considerations of symmetry. In other words, if whatever shape we're considering has an axis of symmetry, then the centre of mass must lie on that axis of symmetry. Then thirdly, use given information about the position of the centre of mass of a triangular lamina and other simple shapes. Well, you have information about various shapes in a published list of formulae that you can use with the examination, so make sure you know what's in there. Then fourthly, determine the position of the centre of mass of a composite rigid body made up by considering bits and pieces, perhaps laminae stuck together, or various three-dimensional shapes put together in some way. So let's look at some key points then. Firstly, when you're considering a lamina, which is a flat shape, we consider it a uniform lamina if the mass is proportional to the area over every part of it. And this means for a regular lamina, maybe something like a square lamina, the centre of mass of that is simply at the geometrical centre of the shape. Same for triangles, rectangles, anything where we could find the centre of the shape geometrically, that's where you'll find the centre of mass, if it's a regular and uniform lamina. For irregular shapes, of course, it's a bit more difficult. Don't forget you have this list of formulae. And now then, for composite shapes made up of laminae stuck together, or other pieces put together in some arrangement, we can find the x-coordinate, for example, by using a rule like this. This means that the sum of all the separate little masses, in other words the total mass, multiplied by the distance to the centre of mass, is equal to the sum for all the separate pieces of their individual masses times their individual distances. And you can do the same for the y-coordinate, but just watch out, because if the centre of mass has an axis of symmetry, don't go to a lot of trouble only to find that the centre of mass lies on the axis of symmetry. You'll only need to do this process in one dimension. And many of the questions we do end with the composite body being suspended from one point. And the crucial thing is that the centre of mass that you've already found will swing round so it ends up lying directly below the point of suspension. And then probably you'll have to calculate an angle. Let's look then at a couple of questions. The first one considers a uniform lamina ABCDE consisting of a square and an equilateral triangle stuck together. Now I'm going to sketch this and just see what we make of it. First of all, we have this equilateral triangle, and that is ABC, and that is stuck to a square ACDE. Here we go then, ACDE. And we've got some information that all the sides of the square are 8 centimetres, which means of course that the edges of the equilateral triangle are also 8 centimetres. And we have to obviously find the distance of the centre of mass, and they've asked specifically for it to be from AC. So I'm going to take moments from AC. That means I'm going to be considering a centre of mass for the triangle that's to the left and one that's to the right. So I'm going to pick a positive direction here because I'm going to need a negative sign later on. Okay, well, what do I know about these pieces? Well, first of all, there's a pretty clear line of symmetry through the middle of this shape. I think I would automatically want to make a point that the centre of mass lies on this axis of symmetry. So all we're trying to find out is how far along, and we're considering it from the line AC. Now it's going to help me just to label another point on there that I'm going to call M, because I want to use some information to find the centre of mass of each of the two parts before I consider it as one whole pentagonal lamina. Well, that's easy for the square, because clearly that distance is going to be 4 centimetres. Slightly more difficult perhaps for the triangle, but there is a piece of information you'll find in the list of formulae that says that you'll find the centre of mass 2/3 of the way along a median from the vertex. Now a median for a triangle goes from a point to the middle of the opposite side, and so it's 2/3 of the way along that line. My problem is I need to find out how long that line is, so I'll calculate that on the next page. Just going to consider again my triangle, and I know all the sides are 8 centimetres, and on this axis of symmetry, where that point I'd called M and this point I'd called, or was labelled B, I need to find 2/3 of the way along. Well, how long is BM? I do know, of course, that it's an equilateral triangle, so I know the angle here, which is where A is. I'll just label that C, by the way. So I know the following piece of information, that BM must be 8 sine 60, and that's just basic trigonometry. And it's going to help me to use exact values here, and sine of 60 is √3/2. Well, of course 8/2 is 4, so the length BM is 4√3. And it's going to help me also to calculate the area of that triangle, because I'm using the area here to represent the mass. And the area of triangle ABC is going to be half the base times the height. Well, I'm going to use AC as my base, and then BM as the height. So it's half of 8 times this height 4√3 that I've found. Well, 8 4s are 32, and half of that is 16. So I make the area 16√3. This, of course, is in centimetres squared, and BM is a length in centimetres. Now, I still need to know where to find this centre of mass. And as I'm going to take moments from the line AC, I'd like to know that length. And that's therefore going to be 1/3 of 4√3. Well, I don't really have a nicer way of writing that except 4/3 √3. Well, I think I'm ready to go then and find out where the centre of mass lies. And I'm going to use considering moments from the axis AC. And just for a moment, let me glance back at the diagram. So we're going to consider to the right the mass acting at this point 4 centimetres to the right, and then the mass of AC of the triangle ABC acting at this point. Now we're using the area to represent the mass because they're proportional. So first of all, I want the sum of all the mass times the distance I'm trying to find, and that's equal to the sum for each separate bit of the mass times its own little distance from the axis AC. Well, the total mass is 64 for the square plus 16 root 3 for the triangle. And that times x bar will be equal to the two separate pieces, the mass 64 represented by the area of the square multiplied by its distance 4 centimeters to the right of AC, and then for the second piece the area is 16 root 3 and the distance we've decided is 4/3 root 3, but as that's to the left of the line AC I need a negative sign in there. It's like the distance is to the left, so that's minus 4/3 root 3. And on the right this is going to work out quite nicely. 64 times 4 is 256, but I have 16 root 3 and another root 3, so there's root 3 times root 3, which will make 3, divided by 3, so this, and that all cancel, giving me 16 times 4, which is 64. And I'm going to just save a step by dividing all of that in one go by 64 plus 16 root 3. And that turns out to be 192 over 64 plus 16 root 3, and calculating that gives me 2.09349, etc., which is 2.09 centimeters to 3 significant figures. And there's my distance. It's clearly to the right of AC, and I've defined that on my diagram and by choosing my direction. Well, there were 5 marks for that, and how were they awarded? Well, obviously you had to do some build-up work finding these distances and areas. So there's a mark for method for a statement like this and filling in the appropriate bits, but of course you have to get the total area correct. That's worth a mark. 64 times 4 is worth another mark, and then this complicated piece here, the 16 root 3 times 4/3 root 3, is worth a third mark. So there's 4 marks really for the method, and then 1 for the final answer, and there's 5 marks for that first stage of the question. Then we have a second part to the question. I'm going to go back to the original diagram, knowing now that the distance to the centre of mass is 2.09. So we've discovered that there's a distance here, 2.09, to take me to the centre of mass. Now we're told the lamina is freely suspended from the point A, which means when it's pinned at this point it'll swing round so the centre of mass lies directly below it on a vertical line. So the dotted line there will end up vertical, B will swing up a bit, and the end ED will swing down clockwise. So the angle we're trying to find is the angle in here, which I shall call theta. Well, we already know that A to M is 4, and we know that M to this point here, the centre of mass, is 2.09. So I'm going to use tan to find that angle theta. And here we go. Remembering from the diagram then, tan of theta equals opposite over adjacent, and opposite was the 2.09 and adjacent was 4. I'm just going to mention, when I worked this out for myself, I still had the exact value of x bar in the calculator, so I didn't lose any accuracy when doing this next step. So theta is inverse tan of 2.09 over 4, and doing all that, hitting equals, gives me a value of theta for 27.6 degrees. And that's the sort of scale that it looked like on our admittedly rough but reasonably decent diagram. And there we go. There were 2 marks for that part of the question, 1 for using tangent and some correct measurements, and 1 for getting this correct angle. Well, there's a 2-dimensional case. Let's now look at a 3-dimensional problem. And I must say, when I first saw this, I thought, oh my goodness, this is going to be very difficult. But actually, because there's an axis of symmetry through this shape, it's not going to be very difficult. We're just really finding where along this dotted line the centre of mass lies, and we're going to, as we did before, consider it for the two separate pieces and then put it all together. So we're given a lot of information. We're given the mass of the conical shell. That's another thing, this is hollow. And we're given the height of it. I know it's lying on its side, but of course that is this measurement, the height. And the base diameter, which of course is the same base diameter as the hollow cylinder that it's connected to. And we have the height of the cylinder. Well, that tells me straight away that I know the distance across to the centre of mass of the hollow cylinder. It's just going to be half of 0.7, so that's 0.35. From the end across there, that's an additional 0.3. So the distance from this point here, which I'm going to label for convenience A, across to the centre of mass of the hollow cylinder is 0.65. Well, what is it for this hollow cone shape? And again, you'll find that if you look up in the formula book, it's as before, 2/3 of the distance from A to that point which lies on the centre of the circular base. Well, if it's 2/3 of the way and the length is 0.3, then this distance is just 0.2. I haven't written meters all over these numbers to save cluttering up the diagram. Now then, let's do the calculation for that. I'm going to move on to the next page for that, but just remember these distances. We have a distance 0.2, a distance 0.65, and the two masses. So I'm just going to record what I know. I have the mass of the conical shell, and we're told that's 0.2 kilograms. And we know the distance from A to x1. Now I'm just going to go back there. I'm going to use a little reference to say that x1 is going to be this point, x2 the point here, and then somewhere over here, I guess, is going to be x bar, or at least the distance from A to that point is x bar, the distance to the centre of mass of the whole shape. So AX1 is also 0.2 meters. And then we had the mass of the hollow cylinder. We're told that's 0.3 kilograms. And we also know the distance from A to the centre of mass of that. It was 0.65, as I showed you on the diagram, again in meters. So if we're going to consider the distances from A, we have, as before, the sum of all the masses times x bar is the sum for each separate mass of the mass times its distance from A. Well, the total mass is 0.2 for the conical shell plus 0.3 for the hollow cylinder times x bar. And for the separate pieces, it's a mass of 0.2 times a distance of 0.2 for the conical shell, plus a mass of 0.3 times a distance of 0.65 for the hollow cylinder. Well, on the left, this is just 0.5x bar, and this gives me 0.04 plus 1.95. I have in total then that x bar equals, if I add up the right side, that's 0.235, and I need to divide both sides by 0.5. That gives me x bar equals 0.47, and what a relief, because they said show that the distance was 0.47. Okay, now let's just talk briefly about the marking for that. There were 4 marks. One was for correctly identifying the distance from the apex of the cone to the centre of mass for the conical shell. And of course, that's just reading it out of the formula book. Then, taking the method here, using the method and having the correct 3 entries in the method are 2 marks. And finally, getting to an answer of 0.47 is worth a mark. Although just writing down 0.47 meters won't get you anything because that's given to you in the question. Okay, let's move on then. And with that information, we're now asked to consider suspending this cone. And this is the bit when I first read it that I thought, oh gosh, this is going to be very difficult. Well, as soon as you've drawn a diagram, it's very, very easy. So don't be put off by questions just because they look hard. Well, I've repeated that part from the question above to remind myself that we know the distance along this axis of symmetry to the centre of mass. It's a distance 0.47 from A. So what are we going to do now? As before, it's going to be suspended, but on this occasion, the object is going to be suspended from this point A, but held so that it remains horizontal by a tension in a cable here. And the question is, what's the tension in the wire required? Well, don't forget that now that we know where the centre of mass lies, we can consider the entire weight to be acting downwards from that point. And we've given the angle 80 degrees here. So what I'm going to do is draw this as a cross-section through the shape so it's completely flat. Remember this image of the 3-dimensional shape, and let's draw it simply as a cross-section. And once again, there's my axis of symmetry, and here, at a distance of 0.47 meters from the vertex, is the centre of mass. We're going to consider the entire weight to be acting through that point. Well, we found that 0.5 was the total mass, so 0.5 g-newtons is the total weight. What's less clear is what's going on here. If it's freely hinged at A, I'm not quite sure what direction to put the force there, or what the magnitude of the force should be. But I do know that there's another force here, which is the tension, acting, and we're told it's acting at 80 degrees. And we have to find the magnitude of T. Well, the simplest thing is to take moments about A, because if that's the point about which we take moments, we can ignore whatever unknown forces or unknown directions of forces there are at that hinge. So let's take moments about A. And of course, if this is going to be in equilibrium, then the total moment will be 0, and we have a clockwise moment due to the weight force and an anti-clockwise moment due to the tension. I need to just work out a little bit more about this tension though. First of all, I need to split it into components because it's at 80 degrees. I'm going to take moments from A, so I'd like to know a perpendicular component of the force. Well, that perpendicular component, if I moved it over here, I would split the force into T cos 80 next to the angle and T sin 80 opposite the angle. So the component acting from this point is T sine 80 degrees. But what is the distance from A to this point? Well, what do I know? First of all, that the diameter of the base is 0.8. So the height here is 0.4 meters from this point to there. And we already knew that it's 0.3 meters from A to this line, which is the intersection of the cone and the cylinder? Well, it doesn't take too much calculation. In fact, don't even need to calculate to know that's 0.5 meters, because this is clearly a 3, 4, 5 right-angled triangle. But if you felt you had to do Pythagoras to establish it's 0.5, that would certainly work. Now let's take moments about A. I think we've got everything we need. So let's consider the component of the tension first. And taking moments, it's force times distance. And I'm taking t sine 80 as my perpendicular component of that force times the distance 0.5. And that's equal to, for the weight force acting through the centre of mass, the force of 0.5 g newtons times a distance of 0.47. And before I go too far, I notice there's 0.5 both sides here, so I'm going to cancel the two 0.5s to leave on the right g, which is 9.8, multiplied by 0.47, and on the left t sine 80. Well, 9.8 times 0.47 is 4.606, although you could leave that part of the calculation until the end if you like, because you'll have to divide by sine 80 in any case, so you might do that all in one step. But that gave me a tension of 4.68 newtons to 3 significant figures. And there's my finished answer. So ultimately, what looked like a difficult three-dimensional question boils down to something that's in 2 dimensions and reasonably straightforward. So where were the 4 marks for part 2 of the question? Well, firstly, 1 was for identifying the distance from A to the point of action of the tension as 0.5 meters. Then, for taking moments about A, there was 1 for the method and 1 for getting both sides correct, and then of course calculating the right answer to be 4.68 newtons. Well, there we go. I hope you found that to be a useful recap for centres of mass. Don't forget to check out the other revision videos for OCR M2.